last time we stopped we weren't able to cover all the material through callbacks, so we'll start there now. First of all, I don't hear anyone. Can somebody verify that they can hear me and that they can see my screen?
Yes, Joseph.
Yes.
Thank you very much. Yeah, okay, so just like FastAI, Keras also has a callback mechanism, and it's very, if you've been through the pain of the FastAI callbacks introduction, which is really not, hasn't been done really that well, at least when I went through it, you'll recognize some of the elements of the callbacks because they do it in a similar way in Keras. So again, they're continuing with the housing data set that we've already worked with. It's a regression model. Remember that that Jerome put together a special housing set data that only has numerical features, and so that makes it easy to make a regression model, and that's what we're doing here. So back to the we build a model just like we have before with a sequential API. You throw in a dense layer. You throw in a pair of dense layers. The input shape is 8 because there are 8 numerical features going in, and the output layer has 1 because all it is that you're predicting the housing price. So that's just one parameter. So that's how you build a model. We've actually done that already. You compile the model by giving it a loss function, an optimizer, and then you can build a callback. It has some built-in callbacks that you can look at, and one of them is model checkpoint. And then you tell it the name of the file that you want to save it in. And remember, this is the H5 format, the high for large files. And you also tell there's a switch there, save best only. So if you go through a lot of iterations, it'll only save the best one and save you some space. All right. So then once you've compiled your model, defined your callbacks, in this case there's just one, then you run the model just like you did before. You run it with the fit method, and the only difference from before is that you include this callbacks. You pass in the list of callbacks. In this case, there's just one element in the list. Then let's see. So this is actually going to fit the model, and then you can load the model that you saved here, and that means you're going to get the best model because that's what you told it to do when you specified that you only wanted it to save the best model. And then you can evaluate the model. So that's what's done here. And I'm not going to run it again because I went and ran this thing later on in the Jupyter notebook. That took a lot of time, so I don't want to interrupt that I don't want to mess that up, so I'm going to keep that. Okay, so we just noticed that we got a loss function of 0.37, and what that means, I believe, is let's see, I think we're using mean squared error, right? So for our loss function, so mean squared error of 0.37. Unfortunately, it doesn't mean too much for us. I think if you took the square root of that, then you'd have the RMS error, and that would be roughly like 0.6. But what does that even mean? Well, the units are in $10,000 as we specified before, or $100,000, sorry. So 0.6, a loss of 0.6 means that your model is only accurate to within $60,000, which is not very good. But I think that's, I mean, it is good in this class of models, with this housing problem. That's a good result. But it just seems that $60,000, an error of $60,000, is a pretty big error to me. Okay, any questions up to here? Okay, and then the next one, they give an example of an early stopping callback, where it's already a built-in, it's already provided by Keras, and let's see, there's a patience parameter, and let's see, and I don't remember what that is, so let's look that up unless somebody remembers it. Let's look up this callback. Let's see what that, remember what that patience parameter is. Okay, so there it is, patience, number of epochs with no improvement after which training will be stopped. So patience equals 10 is a pretty conservative. It's pretty conservative. It's saying we want to see things sort of come to a halt for 10 iterations in a row. So for 10 epochs in a row with no improvement up to this min delta. I think there's a default min delta. We haven't specified it, but how do they decide that? How do they decide that no improvement? Well, they say that the change is less than this number here, this threshold. So if the change is smaller than min delta, that counts as no improvement. And so that's what this patience parameter does. And restore best weights equals true. Let's see what that means. Restore best weights, whether to restore model weights from the epoch with the best value of the monitored quantity. If false, the model weights obtained at the last step of training are used. Best value. Okay, so the default is I'm not sure what the default is. It doesn't say. But in our model, we said that it should be true. So it's going to take the best weights of any of the epochs rather than the weights at the end of the training run. Okay, so that's basically just defining the callback. So we haven't really done any computation yet. Now we do the computation. Model.fit, and we provide the list of callbacks. Now we have two callbacks that we're using, the checkpoint callback and the early stopping callback. So that's how you provide a list of callbacks with the square brackets that denote a list. Okay, and then you evaluate, and here we brought the loss down quite a bit from that last one. So if that was $60,000 error, then this would be more like $50,000 error, because the square root of 0.23 is about 0.5, and 0.5 times 100,000 is 50,000. So it turns out that these callbacks, using both of these callbacks together, it probably in particular the early stopping callback, which we hadn't used before, that's probably the one that is the one that made the difference. So we got the loss down. And now the next example is how to make your own callback. So you define a class that inherits from the callback class, and then you write a method to do some kind of computation. I suppose the method could also produce some plots as well, some graphics as well. But anyway, so that's just one example. And the callback here is to print the ratio of the validation loss to the training loss. And remember that that's usually going to be, we expect it to be less than 1, but we want it to be close to 1 to indicate that we're not suffering from overfitting. So he runs it. Surprisingly, it's more than 1. It's greater than 1. So I'm not sure what's going on there. Oh, I'm sorry. The loss is large loss is worse. So let me back up to what I said before. We expect that ratio to always be greater than 1, because validation loss is always going to be worse, i.e., bigger than training loss. Remember, the low value of loss is good and a higher value is bad. So this is not a surprise. 10% larger. Validation loss is 10% larger. Okay, so that brings to the end of the callbacks. Probably it would be useful to have your own make your own homework assignment and force yourself to write a callback or two just to get in the swing of it. I don't know if at the end of the chapter he has an assignment that does that. But if you have time, I think that would be the best thing to do, is to think up a callback, write it, and make it work. And if you have trouble doing that, feel free to post to the Slack group, and I'm sure that people will jump in and help you if you're having trouble. Okay, any questions about callbacks at this point? All right. Okay, now let's see do we have Mosh with us? No, because he asked a question about, he wanted to see about Tensorboard, and that's what we're going to cover here. So the next section is an introduction to Tensorboard. And so you have to define so again, we're going to use the housing data set. You have to define a log directory where you stick your logs that result. And I labeled this because it's not clear if you don't have that label. The first thing he's doing is he's running the model with a learning rate of 10 to the minus 3, which you can see here. The learning rate is 10 to the minus 3. And then, so you do the same, you do all the steps as before, but when you, but now you write a Tensorboard callback, which is already provided for you, and all you have to do is tell it where you want to put the logs and the run information. So just as before, we fit the model, we run the fit method on the model, and providing it a callback list. And here we're going to include the checkpoint callback and the Tensorboard callback. I'm not sure why we're not including the early stopping callback, since we already showed that that was very effective in getting us down to a low. It was dramatically better than checkpoint callback if you included the early stopping callback. Anyway, so that's that run, 30 epochs, and at the end we have a loss of 0.37, which is similar to what we got with last time when we used the checkpoint callback. Okay, so that's so that's the same as before, right? But now we made that run with the Tensorboard callback, so now we're going to be able to visualize things in Tensorboard, and so it shows you how to do that. You load. You have to. These are the magical incantations that open up Tensorboard for you. And let's see. Oh, how come it didn't? Tensorboard is already loaded. To reload it, use reload. Okay. Let me see. Oh, let's see. It says no profile. I'm not sure why. Okay, I saw, I definitely had a different screen when I ran it last time. Inactive. Oh, I don't know. Capture profile. No. Well, I guess I didn't save, I ran these models down here that took a long time to run, so I don't want to run anything now that would interrupt them. So I hate to, let's see. I really want to show this thing. Oh, well, I think maybe I'll do this. I'll run this because it's a visual thing. Let me just make sure that I'm not going to be stepping on anything graphical down here. No, I think it'll be fine. Yeah, way down here. I'm just going to run this again, this Tensorboard run. So do this. This is pretty quick. So remember, this is just the same model we ran before for the housing data, but this time with the Tensorboard callback and the as well as the checkpoint callback. It's a list of callbacks. Okay, I think it should be done by now. 30, almost. 25. You can see we're getting down to that 0.37 loss that we saw before. Okay, there we go. Okay, so now we can load up the Tensorboard. This time we get a plot. All right, so and what we're doing is we've got the loss function being plotted as a function of epoch, and you can see that it nicely decreases until you get down to about 0.37 at the end, 0.36 or so, and that shows. So that gives you some kind of a graphical output for that run, and I think it's really a lot more flexible than this. There's other things you can do. I haven't really explored it that much. Interesting. It gives you a graph of the of your network. Auxiliary nodes, profile. I don't know about that. Oh, some kind of a projection of the features somewhere, but it's got 3 dimensions. Okay, that's T. So it has tsne and it has PCA and it has UMAP. I have to admit this is the first time I've played with this. The dynamics, I think, is what's happening during the run, during the run, I guess. When things are moving around.
It shows you the iteration on the left bottom.
Oh yeah, okay. And what are we looking at? We're looking at learning rate. Well, learning rate. Oh, this is an adjustment of the learning rate. Huh. So sure. Perplexity. This isn't this isn't a NLP model, so I don't understand what they mean by perplexity. What is perplexity? The most appropriate perplexity, the density of the data. A larger, denser data set requires a larger perplexity. Typical values between 5 and 50. Okay, well, not sure what that is.
Perplexity is a parameter. I don't recall the detail, but it's a parameter used in these UMAP tsne models.
Oh, okay. Is it the same as the perplexity that they use in NLP models, or
no,
a different interpretation?
So, yeah.
Okay.
I do remember that the values, and there is discussion in the book, and even more discussion outside the text of the relationship of perplexity, or what you should use that value as, and how much that helps you cluster using UMAP or tsne.
Mm-hmm. So the thing I'm seeing is that it's very jumpy, and it doesn't change if we change the learning rate. It's still jumpy. I wonder if the other methods are
What is fascinating, I don't know if anybody on the call already knows, but it seems that you can do this. From what you're showing, it seems like you can run and analyze the tsne or UMAP of the data while of what you have already run with an existing learning rate and change the learning rate and see what effect it has through the iterations, which is kind of interesting, right? Because you
So
already specified a learning rate when you
yeah,
ran the notebook, but then it's
yeah.
allowing you to change and rerun it and show you what the layers or whatever you're looking at here change as you fix the learning rate with a new value, and it seems to rerun it.
Isn't that learning rate for TSNE though, and not for the model though?
Yeah, it's only TS. And I mean, the other methods, UMAP and PCA, don't. They're static. They don't allow adjustment, but this one does. Seems like it's more jumpy with the higher learning rate. Oh, maybe not. Anyway, I don't know much about this, but it's fun to play with it. And I guess there's a link here that says tells you how to use it effectively. So that's nice. Oh, what does it say? Oh, it's got its own simulation here. Yeah, so I think what Srinivas said is interesting is that it may be doing something with the data that we passed into Tensorboard from the run. I don't really know.
It's actually, yeah. But Rakil, are you saying that it's not the learning rate that we supply that it subsequently, but it's some other parameter only for that's independent of the learning rate we supply that it uses for TSNE? I thought it was rerunning the data because it has it, and then when you now move the slider, it takes it. But I don't know. We'll have to play with it to determine what it is.
Yeah, for some reason I think that's only TSNE related and not model related.
Hmm.
Yeah, it would be interesting to find out exactly what we're getting from this.
Yeah.
But anyway, it's an interesting interface.
Also, quick question: has anybody run it with Google Drive and Colab rather
This
than on
notebook,
a personal? Yeah, rather than on a.
I haven't tried it on. Yeah, I haven't. But
Because it
people
would
tell
have
me
to.
that it runs much faster.
Yeah, no, I'm saying with the Tensorboard setup and stuff, because then you'd have to configure that to write to your Google Drive, right? Because that's your storage.
Oh yeah.
So I was just wondering whether that setup has any unique complications. He would still have figured it out because he uses Colab notebooks.
Yeah.
But I
I
was just
guess I
curious.
guess if you do that, you have to do. There's some magical incantation that you have to do when you get into Google Colabs if you want to be able to access things. If you want to be able to store everything on your own Google Drive. Then you actually have to log in and get an authorization code and everything. But then once you've done that, you can now access your own. You can save you can save things. You can save the notebook in your own Google Drive, and you can save files in your own Google Drive. So I imagine that's what you have to do
Yeah, that's
to
how I
get the
ran
you know.
all the other notebooks, but I'm just wondering whether there's anybody has run this one and used Tensorboard setup. But anyway, I'll do it later this week. I was
Okay.
just curious whether anybody has already done it.
Okay, great. And then he has another example, and I think the only thing different about this example is that he uses a learning rate of a small learning rate, and I found that, let's see, 0.05. Let's see. Oh, it looks like. Let me try that again, because the first time I tried 0.05, I got all kinds of nans in the result. So so I don't know. He had 0.05, so I'll go back. I thought I had to go up to 0.01 to get it to run. So, but maybe I'm wrong. Let's try this. Okay, so we're doing the same thing as before, except now we're passing in this learning rate in the when we compile, and our callbacks are the same as before. So everything's the same as before, except our learning rate now is much bigger. No, it's running. Okay, good.
Don't specify
Does
any
anybody,
data
yeah.
initialization, so I guess probably that's why you were seeing NANDs at some point of time.
Yeah, I saw NANDs when I tried this first, and so I'm not sure why I'm not seeing them now. But is it, I guess that this whole machinery is so smooth that a lot of times you lose sight of what's going on inside. Like, what is the default initialization? What is the default batch size? I can't remember those things right now. I think it's maybe 32 for the batch size. And I don't remember what the default initialization is. It's some kind of random initialization for sure, but I don't know if it's Gloro initialization or H initialization or what. Okay, so I finished, and let's see. Okay, I guess he wanted to show you that there's other available logging options. I haven't explored any of these. So I guess your log files can have images in them. I haven't really explored any of that. So here's the second run in Tensorboard. And we can compare it with the first run, but we have to see. See, it's giving timestamps on these runs, so I think that we really want the last two runs. What's going on? I don't understand why this run, because I didn't specify any kind of learning rate schedule, at least that I'm aware of, unless this thing is a lot slicker than I even thought it was. Let's see, what does this look like? So it doesn't have any, so apparently it remembers something about 4 runs that I've done. I can't see the time stamps, but the last 2 are the only ones we're interested in, the ones we just finished doing. And I don't understand, I must say I don't understand why the result looks like this. But in the end, you know, it did get down to, oh, this time it got down to a loss of 0.29. So that's better than last time. And I'm not, oh, and so the learning rate must have been better. The learning rate must have had a good effect. What's this smoothing parameter? If I don't smooth, that's just really weird. So this is consistent with what we know about large learning rates, is that sometimes you can bounce around, but apparently the other thing about large learning rates is they get you quickly to the to a local minimum. So it bounced around, but it got back to that minimum. So I guess it was all right. And all this does is smooths out those curves, but so I guess if you wanted to smooth it a lot, you would do that. But if you don't smooth it at all, this is actually what it looked like. And I don't understand why we're not seeing anything for the first run. Oh, I know why we're not seeing anything for the first run, because it's not looking at the first run. It's looking at the last time I ran. It's the last time. See, I called, in this run, I had to define a new log file, right? So we defined a new log directory, and so and so when I go in here, it's looking at the last 4 runs that I did. The last 4 times I ran through this. The only one that's relevant is the very last one, so that's this one. So now we can just remember, so we don't forget, we got down to about 0.29, let's say 0.3, the loss function here, whereas for the last run with a much lower learning rate, we got down to, let's see, I need to get out of this thing. We got down to 0.36. So this run was significantly better with a large learning rate. Remember, the first run, the learning rate was 10 to the minus 3, I believe. Yeah, 10 to the minus 3. So a learning rate of 0.05 made a big difference. So that brings us to the next section on hyperparameter tuning. We've always been told that learning rate is the most important parameter, and now we see it. With the last results that we just got. So we don't want to just guess what the learning rate should be, and so the next section is about hyperparameter tuning. How can we, in a principled way, find the best values of all the interesting hyperparameters that we have to deal with? So we go build a model again, the same way we did before. Let's see, is it the exact same thing? Yeah, it's pretty much the exact same thing. But now we leave the learning rate. The learning rate is initialized to 3 times 10 to the minus 3. We don't really have to leave it there, but let's see. So this is so now we're using the sequential model to write a function that builds our model for us, but it's really doing the same thing, the same steps that we've already done, and then it's just returning the model for us. So it's defining the model just as we did before, and returning the model when you run the function. Now we do something interesting. You have a Keras wrapper that allows you to put a wrapper around this so that you can drop it into. It's a Scikit-Learn wrapper. You build this model and then you build a wrapper around it, a Scikit-Learn wrapper that makes it into a Scikit-Learn object, which can then be dropped into Scikit-Learn pipelines. So this is a really important step here. And there's a special function to do that. Keras.wrappers.scikit-learn. And well, this is a regression model, so we have to use the Keras regressor on it. So pay attention to the syntax of this command. You tell it what kind of a model you need to build, which is a regression model, and then you just plop in the Keras model function, the function that builds the model in Keras. And we're also going to use the early stopping callback. So then the next step is you can you call this model. The model's name is Keras regression, Keras_reg, and then we basically compile that model and then we can fit it. And just as before, when we fit it, we can supply callbacks. And we're going to keep this early stopping callback that we used before.
So would this still be on the
yes.
GPU, or since it's getting off Scikit-Learn, I was just wondering about that. The time looks pretty fast still. It looked like 87 microseconds or something.
87 microseconds. Yeah, I don't know. I don't know if this is on the GPU, but that's a really good question. I don't think it is. Remember that Salim introduced us to this, what's it called? The package. Rapids AI, that package that does the training on the GPU. And so it'd be interesting to experiment with that, but I don't think this does the training on the GPU. Because
building bigger models, then I don't think this would be helpful if that is the case then, right?
You don't think that?
No, if it's still running on the CPU and not the GPU, then if you're building something, even let's say like a convolution neural network, it's going to take forever.
Yeah, I think there must be a way to get it to run on GPU, some setting which configures Keras, because I think at least my recollection of Rapids and even FastAI is trying to get, is already doing stuff with Rapids, is more to parallelize pandas.
Right, but I think Scikit-Learn doesn't run on GPU, right? Scikit-Learn is CPU only, if I'm not wrong.
As far as I know, yeah. And yeah, so it can't be running on the GPU because I have a Windows 10 machine and I don't think I have access to the GPU from here. I could be wrong, but I don't think I do. Anyway, so this model runs and it gets the expected result, something like 0.37. It's we just used the we had the early stopping callback last time and it got much better than. Yeah, I'm a little bit puzzled about why the early stopping callback didn't didn't help us this time, because remember the last time it helped us a lot. What's the difference? Learning rate. Okay, so we haven't done any hyperparameter tuning yet. We've just used the default values of the hyperparameters right now. And we put the default values that here, number of neurons, number of hidden units is only 1. That's probably why we're not getting such a great result here. Because up above, I think we had number of hidden units was 2. Let's check that. Let's see. Yeah, we had 2 hidden units.
I think it's the number of neurons, right? You said 30 there, whereas in the built model,
Yes.
the default is 8.
The 8 is the number of inputs. Yeah, 8 is the input shape. But n hidden is 1, and we had explicitly built a model with 2 hidden layers before. So that's probably why we got a worse result here. Okay, let's see. And I'm not sure why he did it that way. Maybe to make it quicker. And this is just to show, remember we had that x nu was the set of 3 data points that we could then predict on. So these are the predicted housing prices for housing price in hundreds of thousands of dollars for those 3 houses. Okay, so we still haven't done any hyperparameter optimization yet. So he's got he's implemented using randomized search CV. That's a package or a something you can import from a package that lets you do the hyperparameter search. And it's, we've already seen this. Since we now have a model that's wrapped, that has a Scikit-Learn Wrapper, we can use the Scikit-Learn functions that we're familiar with for optimizing the hyperparameters. So this is and we've already seen this. We've done this before, and I think it was back in chapter 2. So here's how you do it. You specify parameter distributions. Now the original code, he had some of the parameters specified in discrete spaces, but other ones were specified as distributions. I crossed out those commands for reasons I'll tell you about in a minute. So instead of having specific values of the number of neurons, he gave a range originally, and then this thing would, by default, search within that range and find the best value. And for the learning rate, he also gave this is kind of interesting, you can actually specify a distribution and a range. So here, he said search between 3 times 10 to the minus 4 and 3 times 10 to the minus 2, but impose a probability distribution on those values, and he's using the reciprocal probability distribution, which goes as 1 over x, remember? So that means small values would have a higher probability than larger values. Remember what the 1 over x curve looks like. So this is an interesting feature that allows you to optimize over a distribution of parameters if you have some idea of preference. So, maybe somebody's practical experience tells them that smaller parameters are preferable, even though we just saw in the work that we did above that 5 times 10 to the minus 2, the largest parameter, the largest learning rate was even better. But the point is that this thing didn't work as is. And see, I had some comments here and they seem to be gone. Oh, here we go. So this is the comment he gave. The following cell crashes at the end of training, and it's caused by a Keras issue, number 13586, blah, blah, blah. And it turns out that issue, if you go there, it's not been resolved yet. I just went there. That should be 9/30th. I just went there today, and it's not resolved. It turns out this issue is also on Hands-on ML2 on the GitHub site. Somebody pointed to this issue, which caused Jerome to go look it up, and then he realized it's not his fault. It's really Keras. The Keras team. It's on them to fix it. So this issue was closed in his GitHub, and he's waiting on them to fix it. So what I did as a temporary workaround, I made all the parameter distributions discrete, and that fixed the problem. I don't understand quite why, but it did. And this is just a note from SciPy Stats that tells you, basically what this reciprocal is. It's just a 1 over x distribution. Well, let's see. Yeah, 1 over x. So, okay. So anyway, I did this and was able to get it to work by substituting these discrete distributions of parameters. So I ran it, and then you can get out the best parameters. It turns out that even though we told it our default was 30 neurons, it turns out that it does best with 5 neurons. It only needs 2 hidden layers, and it likes the learning rate of 0.03, which is kind of like what we saw before. We saw that 0.05 was a good learning rate. So this makes sense to me, this set of parameters. And then the best score was 0.37. That doesn't make sense because we saw a score of 0.29 or something before. So, oh, yeah, we saw a score of 0.29 back up here. Well, even here. So, yeah, there it is, 0.29. And the model was 30. It had 2 layers with 30 and 30, and a loss of 0.05. The only difference between the optimal, quote unquote, optimal parameters is that we had 2 layers of 5. The 2 hidden layers had 5 neurons each instead of 30. So I'm a little bit puzzled about why similar parameters gave us a much better loss when we use the same callbacks. Checkpoint. Oh, here's checkpoint callback. Did we use the checkpoint callback this time? No, we used a early stopping. Huh. Well, apples to apples. I guess we used it. We didn't use the checkpoint callback. We did use the early stopping, but we did see that the early stopping callback gave us even better results than the. Yeah. So, yep. I'm not quite understanding these results.
Aren't your number of epochs different?
Okay, let's check that. Epochs 30. We asked it for 30 epochs. And what did we do before, 50 or?
Joseph,
we did 100.
Joseph, just an observation that in your case, you don't even let the neurons go up to 30.
That's right, because we have early stopping. No. We're setting them at 5. Oh, that's right. We're setting the 5 is the upper limit.
Yeah. So you don't
even let it
get to 30.
Yeah. That's a good point. That's a good point. And maybe that does it. Let's see if we can change that.
If you chose it to be, to include 30 in the range or whatever, then it might.
Yep. Yeah, so what you're pointing out is that we only allowed it to go up to a maximum of 10.
Right.
So now that we know that 3 isn't, we don't need to test to 3. We can go up to 50 or something. Well, let's just go up to 30 because I fear that the higher the number you use, the longer it's going to take to run it. We already know that the low learning rates aren't that great, so we can get rid of that one. Probably should keep those. Let's see. This might take some time though. Let's just see what happens. Oh, didn't like that. And hidden is not a legal parameter. Where am I? Oh, let's see. Did I? I think I run down to here. Nope, I guess I haven't run this one yet. Ugh. Oh well. Anyway, so I have to do this. Clear session, start again. have to run that, and we can talk while it's running. The next thing I did after this was I tried this thing called Keras Tuner, which is supposed to be maybe a better way to. It's more, well, when this book came out, when the Hands-on ML book came out, I think it was already in use, and so because he refers to it at the end of this section. So I just thought it would be interesting to try out at least one of these methods, because he pointed out at the end of the section, he pointed out a whole bunch of packages that do this for you, that allow you to do the hyperparameter tuning. So I just tried out this Keras Tuner. I have, let's see, nope, that's not it. There it is. So, you know, there's information on the website, and it gives you an introduction, and so you can sort of steal some examples. And so that's what I did. I just stole a simple example and implemented it, and it worked okay. But there's a little bit of syntax that you have to get through to make it work. So this thing called, so we're using the same definition for the model that we built before. In other words, we have this function that we built that builds the model for us called build model right here. So that function is the one we're using. Let's see what, oh, this thing finished. Okay, let's see what we got here. Okay, now it's better, 0.28. So Srinivas has caught the error and figured out what was wrong. Now things make sense, right? And what are the best parameters that it found? Well, predictions are similar. This is the one that takes a long time, I think, anyway. Oh, I should have checked what the best parameters were. Anyway, back down here. So this is a different method of doing hyperparameter tuning using this package from, it's one of Keras's package. It's just called Keras Tuner. So we use the same, we have to rewrite this build model function with a little bit of syntax in it. HP is for hyperparameters, and HP is just is an object, as a hyperparameter object in this Keras Tuner. And if you want to provide some values for hyperparameters, you have to go hp.choice and then give it the name of the parameter and a list of values that you want to check. And in our case, we've already dispensed with that, and we already know that 30 is probably a good upper limit. We can give it values for the learning rate as well, and we know that that's too low. Sorry. I did something wrong. These are decreasing order. So 3 times 10 to the minus 2. I guess we could make 10 to the minus 1. Uh, 3 times 10 to the minus 2, 1 times 10 to the minus 3 times 2. So these are probably too small to worry about. We already know that the really small values didn't do very well. Okay, so, you know, in this case, I called the optimizer, and in the optimizer, that's when I gave it the learning rates. So this is kind of a weird trick in the syntax that you have to do. If you want to give it a list of learning rates, well, I guess you could just maybe to make it look nicer, you could write well, I don't know if this will work, but this worked. This syntax worked, but maybe it would look nicer if you could just say learning rates equals that, and then you could say learning rate equals learning rates. Anyway, maybe that's a prettier way of doing it, but I don't know if that'll work. Let's see. Oh, I can't run it because something else is running now. Yeah, I'm still running. Unfortunately, this is the longest. This takes a long time. This hyperparameter optimization. But anyway, I was able to run Keras Tuner, and so the syntax goes like this: you import from Keras Tuner.tuners. You import. It has several of them available, and the one I didn't try anything fancy. I just imported the random search tuner, and then there's the syntax. This is the syntax of the call. You have to tell it what objective function you wanted, and I thought I wanted to use a more informative objective function, and so I chose MAPE, which is mean absolute percent error. Because if I want to make sense out of the error on the housing price, it makes more. I mean, to me, $60,000 is less informative than 15% error. So I wanted it to report the errors in terms of mean absolute percent error, and so I got it to work that way. And because I can't run this again for you, I can just show you what the result was. Oh, let's see. Oh, before I do that, I'll just show the outputs here. It gives you a summary of the search space once you do this, and then you tell it. Then you actually do the search of the search space, and then it comes back with a summary. You can see this part took about 4 minutes. Let's see, and then you can get a results summary. Let's see. Unfortunately, these are not very visible. These cyan colors. There's a way to change it. Would be good. And then you can get out the best parameters. And in this case, because the run I didn't know about the 0.05 rate being so good. So I don't think I let it try rates that low. I mean that high. So it came out with that. That's not really the best learning rate.
Joseph,
yeah.
Wouldn't it try to maximize the objective? So MAP is probably not the best option, right?
I think
parameters to maximize the objective, right?
I still want to minimize. I still want to minimize the objective. MAPE, I want that to minimize.
So have you mentioned it anywhere that, because accuracy obviously you want to maximize and you replaced it by MAPE. So it would try to maximize MAPE as well, right?
That's a good point. Let's think about that. I don't know. Yeah, loss functions are to be minimized. It knows about loss functions, and I gave it that as a loss function, right? So if I give it the MAPE as a loss function, then it's okay because it's trying to minimize it.
Wasn't it the objective?
No, I gave it as the loss function.
Okay.
Let's go back and see that. But that's a good point. I mean, you have to be conscious of whether you want to minimize or maximize the function. Let me just verify. Let's see. I can't remember where I did that now. Let's see. Loss MSE. No, that was above. Loss. This is also MSE. Sorry, go ahead.
Just a command F or search F and then search for objective, the word objective as such.
Yeah.
Good point. Edit. I think it's loss that I want to search for. Let's see, to minimize that. Oh, I know what I want to look for is MAPE. There it is. See, oh, you're right, it's the objective. So, I lost it now. I hate this.
It does minimize it. You can see it right there. Objective val map direction min.
Okay, so it knows that it wants to minimize?
Yeah.
Okay.
I mean, I think it looks at the thing that you're mentioning, and it knows, it's smart enough to realize whether it's to minimize or maximize. Yeah.
Yeah, because these things are defined. I mean, this val mape, it knows what val mape is. It knows whether it's a function that needs to be minimized or maximized. So, but that's a good point. You have to, maybe you have to worry a little bit about whether you're minimizing or maximizing. So, you know, yeah. Okay, let me see where we are here. Is it still running? These things take about, 5 minutes or so. Oops, I'm going too far. I'm not sure where I am now. Okay. Yeah, here it's still running. It's hard to figure out where you are because it's doing 30 epochs of each thing, but there's, for each combination of hyperparameters, it's doing 30 epochs. And so you don't really know how many combinations that it's done out of how many combinations that it still has to do. Anyway, yeah, so back to the Keras Tuner, there's, this is kind of shows the syntax that you would use to do a call to it. And let's see, once you get the best parameters, like we had here, this was the best parameters for that particular run, then you can actually build a model with the best parameters and train it on the model. And that's what I did here. And then, let's see, I think I did it differently. I used mean absolute error as my, I didn't try the MAPE with this run. So I kept it at mean absolute error. And so again, it's like $60,000. So yeah, but the point is that that's consistent with the result we got before with this similar, with these similar hyperparameters. So this gives a different, so that shows that, you can use Keras Tuner to do this hyperparameter search also.
Joseph, you don't have to square it. I mean, this time, right? It's just mean absolute error. So it's just
That's right. The MAPE is just the mean absolute % error. So there's no, you don't have to take the square root. I think it's done. So let's see what
absolute error that you just showed.
Oh, that one is, oh, you're right. You're right. So y, mean absolute 0.34. That's higher. That's a higher error than we had.
It's lower, right? It's just 34,000.
Oh, 34,000, and we had 60,000, right? Yeah, okay, so it was lower. Okay, so this thing finished. The long run finished. We can see what it ended up with. Let's see, is this the one? Randomized search. Is this the one that I just finished? I can't remember. See, rand search CV score, search CV best parameters. Sorry about this. I'm trying to figure out where. I know that it's finished because I see the unfilled circle. So I know that it finished with that hyperparameter optimization, but now I'm trying to figure out where it was. Yeah, it must have been this one. Must have been this one. Although I asked for time, I don't know why it didn't give me a time. Oh, there it did, 9 minutes. So it took about 9 minutes to do this. Okay, so now we can look at the best parameters that it found in this run. 10 neurons, 2 hidden layers, and a learning rate of 0.03. That's kind of consistent with what we've seen before. And the best score, 0.36. And we are using MAPE now, so I think, let's make sure. No, I wasn't using MAPE. This is mean squared error. So this, so far, I didn't change it. So this score, you have to take the square root of it to get the dollars. So that's, again, that's about $60,000, the error. Yeah, this one. So CV best estimator. So you can get the best estimator, and then you can look at the, well, let's see, run search CV.best estimator. I guess that just specifies the best model that we got. And you can also look at the CV score, or you can 0.31. Oh, 0.24. Now I'm not sure about what this number is versus what this number is. There's two things you specify. One is the loss, and one is the metric. And so the loss is mean squared error. Where did we tell it? I don't see where we specify the metric. Callbacks. Anyway, so I have to figure out what this is. What is this, and what is this? And why is it different than this? Anyway, and then we can evaluate on the test set, and now we get a loss of 0.27, which is only a little bit worse than that. So, and 0.27, now it's like $50,000 roughly. The square root of that is in 100 units of $100,000 is 0.5 times $100,000, so it's $50,000. Okay. Okay, well now we're at the point where we can actually run this. Where are we in? Almost. So here we run this build model. This is basically just the definition of our model. And I'm not sure if this change that I made is going to work. So let's just see if it does. It didn't like that. So I'm going to go back and fix it the way it was.
Joseph, it's a spelling mistake. Learning rate.
Oh, okay. Where?
Learning rate.
Learning rate, is it here? Oh, there,
No.
yes, I see. I see. Is that it right there?
Yes.
Okay, let's see if that was it. Ah, okay, that was it. So it's reloading from existing project. And it's reloading with learning rates that I gave it. I don't really want it to use those learning rates, so I'm going to go and delete. See, it stores the stuff away in little subdirectories, and I want to delete those subdirectories so that it'll start fresh. So I have, whoops. I'm just going to show you what I'm doing here. I'm just going to remove this directory, my logs, because that's where the logs were stored, and my dir, that's where it was saving everything. So now I'm going to force it to do this again. So it doesn't get to reload anything. It has to compute from scratch. So now it's doing that. It's running Keras Tuner for doing the hyperparameter optimization. And it's using the more enlightened ranges that we gave it this time, because with hindsight, we know that these are better ranges for the hidden values and for the hyperparameter. And by the way, I just wanted to show you how to implement more than one hyperparameters being adjusted at the same time. So you can actually adjust other hyperparameters. You can adjust the number of neurons as well, but I just wanted to make an example. I thought an example of one hyperparameter with just the learning rates wouldn't be as instructive as an example with two hyperparameters. And once you see how to do two hyperparameters, then you know how to do n you can do any number of hyperparameters, including the number of neurons. You could also figure out how to specify the optimizer as well. That's a hyperparameter too. But we're not using that this way. So in this one, I used MSE, mean squared error, as the loss, but I used MAPE as the metric. So when we look at the MAPE, that's directly interpretable. That's 23% error. Unfortunately, it's still running, but it may, it may take longer to run. It's already 8:30, so I don't feel like to keep you and make you wait for this. But I will post this so that you could take advantage of the little that I was able to do with this hyperparameter optimization, if you wanted to sort of have a head start in your own exploration. So I'll put this notebook on Colab, I think, and then or maybe I'll just make it available from my GitHub, and then you can get at it that way. Okay, any questions? Still working away here.
In the meantime, I had a quick question. Last time we were discussing about how the epoch was shifted by half, right, to account for validation versus training. And I think we had a discussion, and I think Gautam was mentioning that when you train first, like the trained model is kind of behind because you have not yet loaded your weights, whereas your validation is using those loaded, updated weights.
Yes.
And hence it always performs better. Thinking somewhere on that, isn't that always the case with each epoch though? The next epoch when you're trained, the train is still, it does have updated weights, but it doesn't have the updated weights of epoch number 2, right? Like epoch number 2's updated weights would be uploaded only after that, which is what the validation would see. Am I missing something, or is there something else?
I think it's this. It's that the weights that get returned at the end are the mean of all of the mean of all the weights determined by all the batches. So instead of just getting the or let's see, we're talking about an epoch, right? So
weights, right? Not so it won't be a mean, right?
You're right. At the end of an epoch, I think you return the, well, I guess the question is, at the end of an epoch, do you return the mean of all of the batches? I think that's what you do.
No, I mean, my question wasn't that mainly. It's that like the justification or the answer that we kind of came to was that model one, I mean, on epoch 1, training is like starting with random weights. So that's why as you start printing that score, it's going to be lower than the validation because the validation will have the updated weights. But from the way I'm looking at it is that that is true at each epoch, right? At each epoch, your train lags your validation. So is that inconsistent with the explanation that everything needs to be moved by 0.5 or half an epoch or whatever that explanation that was given?
I guess I still don't understand.
We are shifting the whole curve, right? It's not just the first.
That's what I was going to say, that it is doing what you're saying because the explanation offered was only offered to say, why do you see, if I recall correctly, why do you see validation to be better or worse? I forget which direction initially, but the curve, as Gautam says, also is always shifted by half, is his comment.
Okay. So that is the reasoning, right? So the way I understand that makes sense.
Yes.
Yeah. Okay.
Yes.
That's what.
Also, I think we should be looking at steps, not epochs, right? Because the weight gets updated after each step.
True.
And that's a batch, right?
Right, a batch.
It gets updated after each batch.
Yeah. A batch, yeah.
But why? I mean, like, why would you prefer a batch rather than an epoch? Because you wouldn't have run through all your images, right? And then each batch, like your step 1 and step 2, you probably be looking at different images or whatever. Like,
okay, yeah, maybe I'm wrong here.
But at each epoch, it's the update is the weights. You could think of the weights as.
How do we usually plot this? Is it epochs on the x-axis?
Yeah, as far as I remember, it's epochs. Like, yeah, like even fast AI, when you do like 10 epochs, you'd get a tabular of like 10 rows, right? So that prints for 10 rows, I mean, 10 epochs. So at the end of each epoch is what you're kind of looking at.
Yeah, yeah. So the question is, at the end of the epoch, are the weights the most recent updated weights, or are the weights the average of all the matches in that epoch? The
I think it's
averages
the
of all the.
most recent weights, right?
Yep, most recent.
You don't want to average, because imagine if you randomly initialized your weights to start with, and at the end you've trained it well, you don't want to average
Yeah,
and disrupt those weights.
yeah, because at the end is when the weights are most
Updated, yeah,
influenced by
best.
all of the updating. Yeah. So
Though the averaging technique that you're talking of, there is some other optimizer which does that. I forgot what it's called. I think it's called stochastic weight something. Averaging is WA. I think PyTorch has an implementation of that, which pretty much does that. But now, since I say the reasoning, I wonder how that works. Maybe there are some more details to it.
yeah, so we're still waiting for this to complete, but we don't really have to wait. But I thought there was one other thing I wanted to point out. They talked about evolutionary methods to train networks instead, and they recently found that that's an alternative way to train networks, alternative to stochastic gradient descent. And apparently, some of these hyperparameter tuners work on this evolutionary method, which is like genetic algorithms for optimizing. So those are interesting. I didn't have a chance to explore them, but he did mention that in there. Maybe I'll post some links. I'll gather together some links that he mentioned and post them on the Slack. I might have, yeah. I think, yeah.
Sorry, the other thing seems, at least to me, interesting, Joseph, is when he talks about what you have quoted multiple times about batch size and gives both sides of the issue, so to speak, of there are also papers showing very large batch sizes still do good, and if you use learning rate warm up and stuff. So it seems like it's yet another one of these things where the answer is it depends. So there's a whole
Yeah,
paragraph he has on that.
yeah. There's so much of this is an art that gets developed by struggling in in Kaggle competitions, I guess. I mean, people go out and learn. When you're up against a problem and you're obsessed with it, then you start looking for all kinds of things to help you, and then it's kind of like an art. There's you figure out, okay, I'm going to use this technique, and I'm going to use this technique, and I'm going to use this combination of techniques, and this really worked well for me, and so it's still an art, I think, the training of networks.
Yeah, because he says that I thought that was interesting because we had this conversation previously as well of is 32 is larger than 32, and he actually gives the exact quote you mentioned and then gives the counter that there are other papers showing the reverse.
Yeah, and apparently there's something to do with batch normalization. I think if you use different kinds of normalization, you can allow larger learning rates to be larger batch sizes to be used.
Yeah, and also the learning rate annealing, which, given that FastAI does that a lot, that's probably a reason why he tends not to focus too much on restricting batch size to 32.
Yeah, I mean, I think that that if you have, I think he's mentioned, Jeremy has mentioned that you want to use the biggest batch size you can afford in your memory,
Right.
and because the larger the batch size, the more precise the update will be, the more accurate the update will be. Whereas if you use a very small batch size, then the updated weights are going to be noisy.
When we
Yeah.
say 32, that is so image related, right? It's not at all like when you have rows and columns of tabular data, you don't want to do 32 rows. Or for that
Yeah.
matter, RNN
Yeah,
model.
that's right. You can use, that's right. I mean, you can use a lot more than,
Right. So
than 32.
batch norm
Yeah.
also, there are a couple of ways, like you can set up gradient accumulation along with like sync batch norm, which would like calculate your batch norms across things. There are a couple of ways to do that. There's a recent paper with online batch normalization, which literally does one sample per batch. And they have a very nice paper, actually. It's a huge paper where towards the end, they have so much of ablation studies where they've performed better than resonance with batch norms. So yeah,
Can
I
you
mean, at
post
the end
that
of the
on
day,
Slack? Can you post that on Slack,
yeah,
Rahil?
sure.
Great. Okay. Yeah, so here's where he's talking about the different hyperparameter optimization packages that are available. So he lists them all over here, and he talks about the evolution model, the evolutionary search model, and there's this paper where they talk about it. So I thought that was really interesting, and if I have some time, I'd like to just sort of at least get an overview of what that is all about. Anyway, let me just quickly go back to see if we are, yeah, we finished. So let's see what we got. Let's see, make sure I know where we finished, where we were. It's in here. That couldn't have been it. Huh. Oh, there it is. This is the one that took 7 minutes. Okay, so get the results of that and just quickly look at the best parameters. 10 hidden layers and alerting rate of 0.03. That's consistent with what we found before. And I guess this is quick. This only takes about a minute, I think. And we can see that, let's see, about loss. Oh, let's see. I can't remember whether we're looking at MAPE or not. Yeah, we had MAPE here, so how come? Well, I'm not sure why we're not seeing MAPE in this run. Anyway, it's about half done. So this loss is mean squared error. So it's roughly the same as what we've seen before, you know, $50,000 error. So anyway, I guess that's it for today then. And thank you for all staying over. And we'll see you next, or this coming Sunday.